Let me give you some real examples of real materials challenges that we're facing today in nuclear power in this country. So here you can see photographs of all of the nuclear power stations that are operated by EDF Energy in the country. Most of them are called high-temperature gas-cooled reactors. They're advanced gas-cooled reactors. And we have, at the moment, just one pressurized water reactor, and that's at Sizewell. If we look at a schematic of an advanced gas-cooled reactor, it looks slightly different from a pressurized water reactor. And that's because we don't use water to transfer the heat. We actually use gas. We actually use carbon dioxide to transfer the heat. And these operate at much higher temperatures, as you'll see in a moment. But the thing I want to point out is there's graphite in these reactors. And the graphite helps to moderate the nuclear reactor. And it's also a structural component. It's important that the graphite core remains intact. And I've got here some graphite. I won't ask you to touch it because it's pretty dirty, just as your pencil would create a mark, so this stuff does. But this is exactly the sort of thing that's within an advanced gas-cooled reactor. I'll show you a photograph of the reactor core. There you can see it. It's made up of hundreds of these graphite bricks. They're a bit larger than this one. There's an example of a graphite brick. And that core will operate for around about 30 years or maybe a little bit longer if we can keep the thing going safely. This operates about 450 degrees centigrade. As I said, the coolant is carbon dioxide, but also you've got the nuclear reaction going on within the core, and so there are neutrons which are bombarding this core the whole time during the operation, and those neutrons actually change the properties of the material, and we're looking to operate this for at least 30 years. So let's just look at the microstructure of graphite, because we've seen that microstructure affects how materials perform. So that's what graphite looks like, nuclear graphite, under a microscope. It's made up of a number of different components, but the thing I want you to notice is that it's full of holes. It's full of porosity, and actually, not only porosity, but within these coke particles, you've actually got cracks. And that's what the graphite looks like even before it goes into the reactor. But during life, the microstructure changes. In fact, it becomes more porous. The dimensions of the graphite change. It heats up, and as the radiation damages the graphite. And actually, that creep process, that slow, steady elongation of that material I showed you earlier, also occurs in the graphite. So you've got all of these processes going on together, and what we need to try and do is understand those and be able to predict them. Well, the key for doing that is to relate the microstructure to the properties. So what we do now is we don't just look at the graphite in 2 dimensions, we actually look at the graphite in 3 dimensions using something called X-ray tomography. It's just like a CT scan, but on materials. And this is some results of some work we've done here at Manchester. So you can see here all of the porosity in 3 dimensions within a little block of graphite. You can see some of the cracks that I showed you earlier. All of this porosity is connected to each other, but you can see some other porosity out here which is not connected. That's actually quite important when we come to contamination of graphite. So we can build up a very complicated picture of the graphite in 3 dimensions now. That enables us then to take that information and build it into a computer model of the graphite where we can actually calculate how that graphite material will behave at temperature and under stress. And what you can see in this diagram is what's called finite element analysis. So this is a computer simulation of the graphite. And this shows the state of stress within the graphite block. So you can see the stress isn't uniform. It's affected by the microstructure. Well, that little bit of information can then be fed into larger models to predict how the larger brick will behave over time. And that's what this simulation shows. So you can see on the left the brick. Here we've modeled a section of the brick. And you can see the red is where the stress is high and tensile. And blue, you'll see, is where it's compressive. And what you've seen there is that the stress changes through the graphite brick during its lifetime. And all of that information helps us to understand and predict how the core of an advanced gas-cooled reactor will behave during time. And we can predict that out into the future. So that's one example. I want to give you another example related to new nuclear build, because, of course, in this country, we're looking to build new nuclear power stations to replace the advanced gas-cooled reactors that are going to close down over the next 5 to 10 years. So this is a schematic of one of those new pressurized water reactors. You'll see it's pretty much the same as the example we gave you to operate there. So what's the challenge with this? We're using new materials. We understand these reactors have operated for many years. What's there to learn? Well, this is one of the biggest challenges to new nuclear power stations, is actually welding, the way the materials are joined together. Welds are often the weak spot in any structure, actually. It's often they fail at the welds, and there are a number of reasons for that. One of which, the microstructure of the weld is not as well controlled as the parent material, so we have some challenges there. But one of the biggest challenges is, as the weld cools from molten material here, of course it contracts. As it contracts, it sets up internal stresses. And you saw the effect of those internal stresses on that brass tube. And it's those stresses which really cause us a problem, because those stresses can lead to damage and they can lead to cracks forming and growing and cause us difficulty. So again, we're doing some research here at Manchester on trying to improve the quality of welds. So here's a weld. If we took a little section through it and we plotted the state of stress within that, you can see the sort of red hotspots, which is where you've got these very high tensile stresses. Well, what we're trying to do is to design new weld materials that actually convert that tensile stress on the surface, on the outer surface of this, into a compressive stress. And by adjusting the composition of the material, we can actually start to tune the state of internal stress within the welds. And by converting a tensile stress into a compressive stress, we can make a weld that's going to last a lot longer out into the future. So all of that research is now feeding into the way that we manufacture power stations and components in all sorts of industries, actually, not just nuclear industry. So that's the second example. I've just got a couple more examples. So this is Sellafield site up in West Cumbria, where a lot of the spent nuclear fuel is actually stored. There are old reactors there as well. A lot of challenges about how do we clean up this stuff? How do we manage it safely? If you look at some of the buildings there, they've got ponds where nuclear material has been stored for many, many years. That material has corroded and it's degraded within the ponds. And actually, it's quite difficult to understand what's there, what its state is, how do we get it out, and how do we store it safely. We can't send people or divers into those ponds because it's just too radioactive. So what can we do? Well, what we can do is create robots that we can put into the ponds with sensors within the robot to assess the temperature, the geometry, the radiation fields, and so on, remotely, so we don't need to go near the ponds. And this is some work, again, we're doing here at Manchester, and we're testing in ponds like these up near Sellafield. I've put a little movie here of one of these autonomous vehicles. The nice thing about these is you can actually have more than one, and they can communicate with each other. So you can actually have a swarm of these robots that manage their way within the ponds and wirelessly send back data to be stored and understood, and we can actually characterize the materials within these storage ponds at Sellafield using this sort of technology. Okay, so that's ponds, but what's going to happen to the radioactive waste when we've finished with it? Well, the current plan is that we'll store it safely in stainless steel cans, and we'll store those cans underground in a geological repository. And again, there's a lot of news at the moment about where is this likely to be. And that's a big debate at the moment, whether a community would want to have this on their patch. But what are the challenges with those? Well, here is some simulated nuclear waste in a stainless steel container that we've cut open. So you can see what all these little flecks of material here are old parts of these old cores of reactors that have been cut up and broken up and immobilized in cement, and that cement is stored into these waste drums, which are just like a dustbin, really. They stand about this high and about this wide. And of course, if we're going to store this nuclear waste for hundreds and hundreds of years, we want to be sure that the corrosion behavior of this stainless steel is understood and we can manage it. So we're doing work on what's something's called, it's called stress corrosion cracking. This is where you get a corrosive environment and you get stress and you can form this sort of crack within here on the surface. And we need to understand what environment causes this and how can we control that. And of course, now these days, we like to look at things in 3 dimensions because they give us much more information than just a 2-dimensional plane. But even more than that, we can actually look at the very tips of these cracks, at the microstructure and of the chemistry at the tips of these cracks to understand the mechanism by which those cracks grow. Because if we understand the mechanism, we can actually design our materials in a better way so they're resistant to that mechanism by changing the composition a little bit or by changing the microstructure or something like that. So there's a lot of work that goes on in nuclear waste containers as well. So again, what are the key messages from that part of the talk? Well, the behavior of materials is absolutely critical to nuclear energy. In fact, to all industries, be it aerospace, be it aeroplanes, as you saw, be it cars, be it railways, be it power stations of whatever type. But it's critical for nuclear energy. It's critical because we need to manufacture power stations using improved materials and improved welding techniques. It's also critical because we want these things to perform safely over their lifetimes, so we need to understand it and we need to be able to predict it. And also it's critical for nuclear waste and decommissioning of old reactors.